Before we can start talking about data structures, or before we can start really thinking in detail about data structures, we need a model of the computer's memory. We need to be able to understand how a computer program uses memory. And we have this basic idea of memory as a table of data where we can store things and we can retrieve things, we can read and we can write. But in practice, when we're writing computer programs, we don't think in terms of those primitive memory operations. We don't think about reading and writing to memory. We don't think about managing the memory addresses of where we're reading and writing. So what we're going to do in this video is develop a more abstract model that's closer to how we think about memory when we're programming. It's closer to how a computer program uses the memory versus how the computer itself uses the memory. What we're going to do after we've written this code in Python is do almost exactly the same thing, but from a different perspective. We're going to take our table model of the memory and think about how the instructions we're writing in Python affect that model of memory where we're reading and writing. And then we'll think at a more abstract level the same instructions again a third time, but at a more abstract level where rather than thinking about reading and writing, we're thinking about objects, variables, and references. So to begin with, we're going to use an example of a simple vector where we have an x-coordinate. So let's say x is 42 and a y-coordinate where y is 17. And here we're using variables to store data. This is almost the simplest thing you can do in a programming language. Clearly, this is not good enough if we want a lot of vectors, because if I have one variable called x, then I can't store more than one thing there. If I have one variable called y, I can't store more than one thing there. So this, what I have so far, is not enough for me to have more than one vector. I can only have one vector this way. If I want more than one vector, then we can define a class. So let's say I have a class called vector, and the constructor for this class is going to take an x and a y as its input, and what we're going to do is assign the input x to this field called x and assign the input y to this field called y. So this is a very normal way of writing a class. All I have is a class with a constructor that will take these two values and it will store those values in the object when I create an object. To actually create an object like this, let's say I'm going to have a vector called p. And p is going to be a vector with the values 42 and 17. Now, if I ask what p is, then in Python we would see that this is a vector object. And this vector object will have the fields x and y, so I can see that p's x field is 42 and I can see that p's y field is 17. There are other things that we want to be able to do with a vector, so I might want to be able to change its coordinates. One of the things I can do with a variable is change its value. So I could, if I wanted to move this vector right by 6, for example, then I would do something like x plus equals 6. And now x would be 48, so this would now represent the vector 48, 17. That's using variables. I can do the same thing with objects. If I say p.x plus equals 6, then I've moved the vector p right by 6. And then if I see what is p.x, that's now 48. And obviously this doesn't change what p.y is. So things get a little more interesting when I start thinking about how to copy vectors. Because suppose I do this naively, and let's say I want a vector called q. So let's say q is equal to p. I'm going to take a copy of p, and then I have this vector q. In fact, it turns out that this hasn't actually copied the vector p, but we'll see why that is a lot more clearly when we start thinking about the memory model. But let's just see what Python is going to do when I interact with this vector object here. I have this vector object called p, which has the x-coordinate 48. Because I've said that q is equal to p, then q's x-coordinate is also 48. But if I change q's x-coordinate, let's say I change it to 15, I'll be able to see that I've changed q's x-coordinate, but p's x-coordinate is also now 15. Now maybe you've seen this kind of thing before, maybe you haven't seen this at all, in which case it would be quite surprising. But this is just something we have to understand about how variables, objects, and references work in programming languages. And if you haven't seen this before, then it might be difficult to understand why this would happen or in what circumstances this would happen. If you have seen this before, then maybe it's still quite difficult to think about, because the way we're interacting with these objects is by writing code and seeing what the results are. So let's now think about exactly the same steps that we've just taken, exactly the same instructions, but from the table model of memory. The first thing we did was create variables called x and y, so I'm going to do that now. I'm going to have a byte variable called x. I'm just going to use bytes because that's simple. It means an 8-bit value, so we're using 8 bits here to store this number. And we had a variable called y, which held the value 17. So we've created this variable x. It's allocated a memory location to hold the value of that variable. This table shows the value in hexadecimal, but if we take a look here, we can interpret this as the number 42. This 2a here just means 42 in hexadecimal. And then the value 17 is being stored in this variable y, which is at the address fe. So the computer's chosen this address to store the variable y. This model is actually choosing these addresses randomly. That's not an accurate model of how a computer works, but it's good enough for our purposes. As far as we're concerned, it doesn't matter where something is stored in the memory. The computer's job is to work out where to store things in memory, and we don't think about reading and writing or memory addresses. The next thing we did was create a class called vector so that we could have a vector object with those two fields. And those two fields both held a number. So let's say that this object holds 2 numbers, and those numbers are going to be bytes again. What happens when we do this? We create the object, we store the values 42 and 17. So those are stored in the fields of that object, and what's actually happened is that the computer has decided to use these 2 memory locations to store the object. It's chosen the address 4a for the object, and it's stored the values of those fields in those 2 memory locations. And this is not quite all we did. We created a variable called p to hold this object. But you'll notice there's no button here to create a variable to hold a vector or an object. In fact, p does not hold the object. What it holds is the memory address of the object, so that I can use the variable to find the object. So let's create a pointer called p, and this pointer will hold the address 4a, which is the address of the object. What we then asked was, what is p? And we said that p is an object, but that's not quite correct, because p is actually the address of the object. It's a pointer to the object. And when we said, what is p.x, we saw the value 42. How is that 42 actually achieved? How do we get the 42? When p holds the address of the object, that means we need to read this address, 4a, go to address 4a, and because x was the first field of this object, we would read the 2a here, which is hexadecimal for the number 42. Now we also wanted to be able to change the contents of these, so what actually happens when I add 6 to x is that this value in the memory is set, it's written, and when we change the value of p.x, what's actually happened is because p holds the address of the object, we follow that address, 4a, that's here, and then we changed x, which is the first coordinates. 4a is this object here, so the first coordinate, or the first field, was this one. If we add 6, then it becomes 48. So what's happened is that we've changed this memory location to write the 48 there. Now that's not obvious that this is what would happen, because we changed p, or we thought we were changing p. If I say p.x plus equals 6, we added 6 to p.x. But p hasn't changed. There's nothing changed here. P still holds the value 4a. What's changed is over here, which is the field of the object. The next thing we did was create another vector variable, q. And we know that q can't hold the vector, it can only hold a pointer to the vector. So let's create another pointer variable called q. And we said q equals p. That means we copy the value of p, and we assign that value to the variable q. Again, what's happened is the computer has allocated a memory location to hold the variable q, but the value of this variable is the address of the object. So the address is 4a, which is the same as the address that's stored in p. There is no extra object here. There is still only one vector object. And then when we set q.x, if I say q.x equals 15, what happens is we read the address from q, we go to this address 4a, we set the x-coordinate to be 15, so 4a is this object here, let's set the x-coordinate to be 15, and that's written the 15 to this memory location. 0f is hexadecimal for 15. And now it's a lot clearer why this changed the value of p.x as well as the value of q.x, because there is only one vector object here. The address stored in p is the same as the address stored in q, so certainly when I follow this address I will find the same object, which is the one that I've just changed the x-coordinate of. If what we actually wanted was a copy of the vector object, a second vector object with its own x and its own y, then we would have to create another object. So now I have a second vector object, I can give it its own values. What we did was copy the x-coordinate from p and the y-coordinate from p. And then we also assigned this object to q. So we said we're creating this new object and we'll say q equals vector p.x, p.y. So this address now should be stored in q. That address is 6a. And now when I change the value of q, if we set q.x equals 59, then it's this memory location that changes. Because q holds the address 6a, I read the 6a, I find memory location 6a, that's this one, we set that to 59, which is 3b in hexadecimal. And now when I read q.x, I would get the 59. But when I read p.x, p holds the address 4a, so I would be looking at this location, 4a. X is the first field, so I would read the 15. So this hasn't changed. The final thing we did was create a class called circle with two fields, one for a vector, the center, and one for the radius of the circle. The center of the circle was a vector, but as we've seen, a variable or a field can't store the vector object itself, it just stores a pointer to the vector object. So this is what a circle object looks like. It has a pointer to a vector, and it has a byte for the radius. Now the pointer pointed to the vector p. So that means I'm going to copy the value of p and store it in the pointer, store it in the center. This pointer is to the center of the circle, which is a vector. It holds the address of that vector. And then we set the radius to be 10, so we're storing the number 10 in the second field. The next thing we did was read the radius of this circle. To do that, we used the variable c. That means we need to create this variable in this diagram. C holds the address of the circle, which is b0. So when we said c.radius, we read the value of c, which is at address 57, that's this one. b0 tells us the address of the circle object, which is here. The radius was the second field, so that's this one. We read the second field of this object, which is 0a, or if we convert the hexadecimal to decimal, then that gives me the number 10. The next thing we did was read the coordinates of the center of this circle. So this is where it gets a bit more complicated, because the variable c holds the address of the circle, that's b0, so we follow that address. The center of the circle was stored in this first one, which is 4a. That's the address of the center, that's the address of the vector. So we follow this pointer to 4a, and then to read the x-coordinate, which is the first field, that's 0f in hexadecimal, or 15 in decimal. So we have to follow several pointers to actually read c.center.x. So all of this is very basic, There's only a few things that can happen here. We can create variables, which means we have a memory location to read and write from. We can create objects, which means we have enough memory locations to store the fields of that object. And we can follow addresses, so I can store the address of an object in a variable or in a field. So this field here stores an address. Some of these fields store numbers, so we have to know what type of thing we're dealing with. If I know that this is a circle, then I should interpret this as a pointer rather than a number. But it's hard to make sense of this kind of diagram just because it's just a table of numbers. It's a table of data, and that's at some level all memory is. The computer itself definitely has to do all of this, but a programmer shouldn't really have to think about all of this. It's a good way of answering questions like, when I say q equals p, and then change q.x, why does that also change p.x? Hopefully now we can understand that kind of thing. But this is a bad way of understanding data structures in general. So this simple data structure we had of a circle which has a reference to the vector object and then a number for the radius, it's very hard to make sense of how that data structure works, what we would do with it, or how we'd use it to solve problems, if the table model of memory is what we're using to understand data structures. So now let's move on to the third way of thinking about this, which is what's called box and pointer diagrams. So let's start from scratch using the box and pointer model rather than the table model of memory to understand what was happening when we wrote that Python code. So let's start by creating the vector object, which is an object with two fields that both hold numbers. We gave those values 42 and 17 for the x and the y, and we created a variable p, which held a pointer to that object. This object is at the address 4a, so in principle, this variable holds the address 4a. But it's much easier to think about this variable as holding a pointer, or the start of an arrow, to this box that represents the object. This variable holds a pointer to this object. So to read p.x, I would start at p, follow the pointer to the object, and then read the part of the object that represents the x field. The first part of the object in this case, because x is the first field. If I wanted to change the value of this field, then what's actually happening in the memory is we start at p, we're setting p.x plus equals 6, start at p, follow the pointer to find the x field, and then add 6 to the value that's stored there. This is still a memory location under the hood. We don't really need to think about it as a memory location when we're thinking about box and pointer diagrams, but we do need to understand that it behaves like a memory location in the sense that it can only hold one value at once. The next thing we did was create a variable called q, and we said q equals p. So we copy the value of p and store it in q. And that means q also holds a pointer to this object. So to read q.x, we would follow the pointer starting at q, follow that to the object here, and see that the x-coordinate, the first field, is 48. That's much easier than thinking about this in terms of finding the right address, if instead I think about it as following the arrow that starts in the variable q. And at this point we change the value of q's x-coordinate. So if I follow the pointer from q to this red box here, change what's in the x-coordinate to 15, now it's a lot easier to see why this also changes p's x-coordinate. So if I follow the pointer from p to find the x-coordinate, that's now also 15. The old value is gone. If I didn't want this to happen, I would need to create a second vector object, copy the values across from p. This was vector p.x, p.y. And then we said q equals vector p.x, p.y. So we assigned the variable q with a pointer to this new object. And now when we read q.x, we would be following this pointer instead to find this 15. If I read p.x, we're still following this pointer to find this 15. That means if I change q.x, follow this pointer, find the yellow object, change its x coordinate to 59. So q.x is now 59, but p.x is still 15, because p still points at this other object. We've changed this one, not this one. Let's finish up with the circle example. A circle had a pointer to a vector, that's the center of the circle, and then it had a radius, which was a number. So here's the circle. The center of the circle was p, so let's copy the value of p and store that as the first field in this object, and the radius was the number 10. So at this point, now we have an object that holds these two fields, but the first field is now a pointer to another object. And we said c equals circle p10. So we have a variable called c, which holds a pointer to the new circle object. So now let's think about what happens when we read c.radius. I start at c, I follow the pointer to the object that c points at, and the radius was the second field, so I read the 10, so c.radius equals 10. What if I want to read the coordinates of the center of c? Well, c is a pointer to a circle object, the center is a pointer to a vector object, so I follow another pointer to find the center of this circle, and then read the x-coordinate of this, so the center of c has an x-coordinate of 15, by following two pointers to do this. So that covers all of the code that we've went through in Python, using the table model of memory and using the box and pointer model of memory. So let's bring this full circle by showing that a box and pointer diagram is a useful tool for thinking about programming. We're going to write the same Python code as before, but at the same time we're going to keep track of the program state using a box and pointer diagram. The first thing we did was create a class called vector. This is exactly the same as before. We said p equals vector 42, 17. In the box and pointer diagram, that means we created a vector object which is represented as a box. This box should have two parts, the two fields x and y. The first field is going to hold the value 42, and the second field holds the value 17. We also create a variable called p, which holds a reference to the new object that we created. If I do something like p.x plus equals 6, which is the same as before, what happens is we replace the old value in this field with the new value 48, because that's the x field of the object that p points at. Next we said q equals p, which means we have a new variable called q, which has a copy of the value of p, which is a pointer to this object. So it's a copy of the pointer to that object, which is a pointer to the same object. Now if I change q.x to 15, it's clear what's going to happen on this diagram. Q points to this object. Here's the x coordinate. We replace the 48 with a 15. Now when I read p.x, there should be no confusion that this gives me the answer 15, because the box that p points at does have 15 in its x field. The next thing we did was say q equals vector p.x, p.y. So there's several things happening here. Let's break it down. We're calling the vector constructor to create a new vector object, so we need a box to represent the new object. This new object has the two fields for x and y. the values for these fields are copied from p.x, which by following p gives me 15, and p.y, which by following p gives me 17. Then we're assigning a reference to this object to the variable q. We create the object and assign a reference to the variable q. That means wherever q was pointing before, this value will be gone, this pointer will be gone, and q will now point to the new object we created, because that's what we said should happen. Now when I say q.x equals 59, we follow the reference from q, follow the pointer from q. X is the first field, so we delete the old value and replace it with the new value. So it should be completely clear from this diagram that if I say p.x, this will still be 15, because following the pointer from p gives me the value 15. The next thing we did was define a class called circle. So this is exactly the same code as before. It has a center and a radius. And we said C equals circle with center P and radius 10. So again, there's several things that are happening here. Let's break it down. We're creating a new circle object because we called the circle constructor. So there is a new object. We need a box to represent that new object. A circle has two fields, center and radius. The first field, center, holds the value of P. P's value is a pointer to this box, so this field for the center will hold a pointer to the same box. It's a copy of the pointer from P. The second field will hold the radius, which should be 10. Then we also created a variable called C. We create the object, then we create the variable C, and C holds a reference to this object that we've just created. At this point, we can ask, what is C.radius? And this should be 10. From the diagram, we expect the answer to be 10, because if we follow the pointer from C, radius is the second field, which is this second part of the box that has the value 10. If I ask what is C.center.x, we can use the diagram to answer this question as well. Follow the pointer from C. Center is the first field. That's a pointer. To find the x field, we follow this pointer. X is the first field, so it's the first part of this box. And that has the value 15, so we should be able to predict that this gives us 15, which is correct. Now if I do something that we didn't do before, if I say p.y equals 80, we should be able to predict what will happen if I ask what is c.center.y now. So let's think about what's going to happen. First, we've set p.y to be 80, so we follow the pointer from p, that's this object. We're setting the y, which is the second field. So we're replacing this 17, whatever value was there before, with the new value 80. So that's the line p.y equals 80. Now when I get c.center.y, let's make a prediction. C.center, we need to follow the pointer from C. Center is the first field, so that's this value here, this pointer. To get the y of this center, we need to follow the pointer to get the vector. This is the object that represents the center of the circle C, and the y field has the value 80. So this should give me the answer 80, and that's what it does. So let's wrap up this video with some rules for drawing box and pointer diagrams. So the first rule is that a box and pointer diagram only has 5 kinds of thing, and these are boxes, parts of boxes, variables, pointers, and primitive values. So let's explain why that's the case. A box represents an object. A part of a box represents a field. A variable is a variable. Pointers are also called references. We usually think about them as references rather than pointers. A reference meaning a way of accessing something, a way of finding something. And the primitive values are things like numbers, booleans, characters, any individual primitive type of data. And there is a fixed set of those primitive values or primitive types that depends on which programming language you're using. But we'll usually say that numbers and characters are the primitive values. In some circumstances, we might think of strings as primitive values as well. So the next rule, a field or variable, so a field being a part of a box, always holds either a pointer or a primitive value. And there is one special case of this, which we didn't come across in this video, which is a null pointer. The reason we might have a null pointer is if we have a variable with the value like none in Python. None is a special value that indicates that there is no object being referenced, or usually some absence of a value in Python. The reason we might want to use this is, suppose we had a circle with no center, then I might say C equals circle none with a radius of 10. And in this case, none would represent the null pointer. What that would look like on a box and pointer diagram would be the circle object with its 2 fields, and the radius would of course be 10, but there would be no center of this circle, so there's nothing for this field to point at. So in that case, this is a null pointer, so it would say there's nothing here. This slash here represents a null pointer. So a null pointer is represented by a slash. Next rule. A pointer can only point at a box. That's an object. So we only access objects by reference. We can't point at part of a box. We can't point at a field. A pointer can't point at a variable. It can't point at another pointer. It can't point at a primitive value that's being held inside a field. Another rule is that multiple pointers can point at the same box. We can have multiple references to the same object. One of the more subtle points is that when we're accessing fields in an object, we have to do that using a pointer. So we can only access fields in an object if we have a reference to it, or if we have a reference to that object. If we don't have a reference to something, then we can't access it. So that means in situations where we did something like c.center.x, we couldn't jump directly to the x to read there. We have to follow the pointers from the c to find the circle object, then the pointer to the center, which is a vector object, and then we can read the x field of that object. So we can only access fields in an object if we have a reference to that object. And then finally, if we're using a box and pointer diagram to show the state of of a program at some point during the program's execution, then the state will be different at different times, so it can be updated. So we can think of a box and pointer diagram as a dynamic diagram that shows the state changing over time. We could animate a box and pointer diagram to show what happens as a program is being executed, but each individual diagram only shows it at one point in time. I'm going to wrap up this video by showing you what I think is a very useful tool for investigating box and pointer diagrams or data structures, or really anything else in Python where this visual model will help. And this is a tool that will show me a box and pointer diagram of the program state live while I write the code, much in the same way as I was writing code in idle and drawing a box and pointer diagram by hand. And actually the first thing you can see already is that when I declare the class called vector and the class called circle, that these are actually variables that reference an object that represents the class. This is just actually a detail of how Python works, because in Python a class is actually an object, and this class name is actually a variable that references that object. But that's a detail specific to Python, and it's usually not important, so I'm just going to hide these. But we can just briefly walk through the same code again to demonstrate what this tool is going to do. So we have a variable p which holds the vector 4217. And we can see that I've got this variable p which references this object. This is drawn in a different way to the way I drew my box and pointer diagrams, but we can see it's the same kind of diagram. We still have the boxes with fields, we still have variables with pointers. If I say p.x plus equals 6, then we would expect to see this 42 change to a 48, which is what happens. If I say q equals p, then we get another variable q, which has a reference to the same object, which is what we thought, that's what we saw before. If I say q.x equals 15, then it changes the x-coordinate of this one, which is the same as the one referenced by p. If I say q is a new vector from p.x, p.y, then I'm going to get a copy of that vector, which is what I see. There's a new vector object that's just appeared, which has the same values as the other one, and now q holds a reference to this new object. If I say q.x equals 59, then that will change the new object that q points at, rather than the old one that p still points at. If we create a circle with center p and radius 10, then we'd expect to see something like this, where I have the variable c pointing at the circle object. The circle has a center and a radius. The radius is 10, of course, but the center is a reference to this vector object, which is the same as the one that p points at. So that's just a brief example of what this tool will do. You can find a link to this tool underneath the video. There will also be a link to the interactive memory model that I used in the video. But that's it for this video lecture. After this, we'll use box and pointer diagrams as a tool to investigate data structures.